Yeah.
Ivy.
But you're good. They're like
Ivy,
yeah.
Nita, Nitya. Winston?
Yes.
Abel?
No, yeah.
Abel, okay. All right, anyway. First, some housekeeping issues. So I have put up the video is up for Wednesday if you wanted to see that. So that's just a link here under the video column. And then also the lecture notes, basically the ones that I scribed, are here too. So you should all have access to those. It'd be worth checking and making sure that you do. And the lecture notes you guys also have comment and edit access to. So in general, you should, as you're reading those lecture notes, make corrections as necessary, or at the very least put comments in there, like, you know, if you have some sort of a question, so that the original author or someone else can address it. And then the scribe, this is a new column, that who's going to be the scribe for this particular lecture. So when I sent that out, I said, you know, after class today, people will be able to add their names for that. Okay, so there are probably 27, I did 2, 25. There's like one free slot. So make of that what you will. And I guess it's first come, first serve. I don't know quite what the right way to do it is. If there's a particular time that works really well for you, then go ahead and sign up for that soon. But my goal is after today, we'll just have that filled out. And then from here on out, we'll be able to, whoever's turn it is to scribe will do that. So I'll be scribing today's, and then you can see basically what I did as kind of an example of what to be done. Let's see, are there any other housekeeping issues? The permissions to edit this file as well as editing the lecture notes are based on a Google group that I put in the syllabus. So you should all be members of that Google group. I know somebody, was it Jason? Yeah, you had sent me, for some reason we had a funny email address, so I added you. So that's definitely something to try and check soon to make sure that you can edit this. And I guess if you put your scribe, if you could successfully put your scribe on here, then you're fine. Okay, so this is a question that I got in the first college calculus class I took. And it seemed like a very simple question. Well, it is a simple question, no matter what. But the answer seemed very simple. So what's the next value in the sequence 1, 2, 3, 4, 5, 6? Anyone? 7. Seems straightforward. But what my professor showed is actually, so what the assumption here is we have some f of n is equal to, let's say that this is element number 1, so f of n is just equal n. That's kind of what we're assuming is the formula for this. But he said, no, this is the formula I had in mind. F of n equals n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5 times n minus 6 plus n. So the first term, if n is 1 through 6, is 0. And then we just add in. So we get 1, 2, 3, 4, 5, 6. I guess we're going to get 5 factorial. No. F of 7 is going to be 6 factorial plus 7, which is 5 factorial is 120, so 727. Now why, and I can also remember, maybe 4th grade? I think it was 4th grade, where we had to come up with this same sort of idea. As you would provide a sequence of numbers, and your classmates would try and guess what the next number is, and you would have written down a formula kind of what it is. And why does this formula that my professor provided not seem fair or proper in the spirit of find the next number in a sequence. Evan? Yeah.
You only have 6 terms to go off of, so if you have a high enough order polynomial, you can make that last like anything.
So the calc prof, yeah, we could have said that. In 4th grade, we wouldn't have been so good at the okay. Yeah. Okay, so, and that is certainly where we're going to be going here. If we have a high enough order polynomial, we can do whatever we want. Another way to phrase that? Or another way to look at it? Chelsea?
It seems unfair because it kind of takes advantage of someone's intuition. It makes them think that they know what will be.
So you lead them down the garden path, and then you yank the rug out from under them, if we look at mixing 2 metaphors. Yeah. But why, what is it about this that led you down the path? Why did you think the next number is 7? Why did you think this is a more natural formula than this?
Like Occam's razor.
Yeah, Occam's razor is probably a good, just happened. So Occam's razor, right, basically says this is William of Occam or something, or basically says something like, I think the simplest description of it, and it's good to have a simple description since it's Occam's razor, is prefer simpler explanations. Right, so if your explanation of why there's a car in the front driveway that I don't know, well, you know, it's not my car, why is there a car in the front driveway? It'd be a more complicated explanation to invoke aliens, let's say, than it would be someone stealing a car. So here, which is simpler? Which formula is simpler? The first one, so that's the one we should sort of assume, right? All right, so that's going to just give us a flavor of where we're going in parts of today. So we can look at a neural network as a universal function approximator for computable functions. Okay, so universal, meaning it works for all functions, but what do I mean by an approximator? Yeah, you can get as close as you'd like to the true function at a price, right? There's no free lunch. And so the cost is an exponential number of neurons. You can even do it in a one-level deep network. If you're willing to have an exponential number of neurons, then you can approximate any function you'd like. And that's basically what we're doing when we're doing deep learning. We are adjusting the weights of a neural network such that it approximates the function that we desire. So in the case of the cats and dogs, what sort of a function did we have that we were trying to approximate? That's like, what's the domain and what's the range?
255 by...
Yeah, it'd be a set of, I'm going to say it's not really reals because it was integers, but let's just say reals. And whatever the size of the image was, let's say it's 300 by 300 by 3. So a fairly large number of inputs, right? And into 0 and 1 is the two possibilities. Yeah, from 0 to 1. So the closed interval from 0 to 1. Okay, so I mean, there are a lot of such functions, right? We could combinatorial figure out, given we have so many inputs. I mean, this is a lot of functions. So the function we're trying to approximate is one that takes cat images to things to close to 0, right? Or, sorry, take it back. The function we're trying to approximate takes cat type images to 0 and takes dog type images to 1. And what about other sets of input, which are in reals, which have 300 by 300 by 3 of them? We don't really care. Right? It's going to take us to somewhere in 0 and 1, and we don't particularly care. The domain we're interested in is cat-dog images. And it turns out neural networks are pretty good at that, and pretty good then at generalizing to unknown inputs, because we're going to just be sampling particular inputs in our space. Right? We're going to be ignoring lots of inputs, like almost all of the inputs, which just look like, you know, a smear of, it's whatever the white noise equivalent is in images, right? That's what most images are going to be, staticky. But for a small subset of them, the cats and dogs, we're going to be taking an even smaller subset of those, some particular cat-dog images, and we're going to find that a neural net does a reasonable job, and we don't really quite know why, of generalizing to unknown cat and dog images, ones that it hasn't seen. So does the concept make sense? So when we are creating a neural network, we're going to come up with an architecture for it, and we'll talk about that some more. We talked a little bit about that last Wednesday, where we have layers, right? We know how many inputs we're going to have. It's however many inputs there are in our function. We know how many outputs we're going to have. It's the output that we desire. So if we have a binary classification problem, how many outputs are we going to have? 1, and it's going to be in the range? 0 to 1. So if we have binary classification, we have 1 output, and it's in the range 0 to 1. If we have a multi-class classification, okay, that is, instead of just recognizing cats, dogs, recognize cats, dogs, pigeons, and snails. Say that again? We're going to have, yeah, so how many outputs are we going to have, given that we have 4 classes? Yeah, we could do 4. Theoretically, we could get by with just 3, right, because the 4th one will sort of be constrained, but let's do 4. So 4 outputs, each in the range 0 to 1. And if we're going to interpret these as probabilities, we want the sum of the outputs to equal 1, right? So we can get any particular image in, and when we look at the probability that it's a snail, that might be, you know, 0.7, because it's a snailish image. And the probability that it's cat, dog, or whatever that other thing I said sums up to the remainder, like the complement. What if we have not a multi-class, so greater than or equal 1 label? It's really greater than or equal 0 labels. So we have, let's say, 100 possible labels. And we want to know any of them that are in this image. So you remember we saw one of the pictures the other day, which was a cat and a dog? We'd like to say, yep, there's a cat. Yep, there's a dog. What would be different from the multi-class classification? I'm going to say we still have the same number of outputs, the number of labels. Yeah, Jake. The outputs no longer summed on. So the outputs would all still be in the range 0 to 1 because we're interpreting these as probabilities. And the sum of the outputs, let's just say the sum outputs equal 1, we'll just get rid of. Right? I don't really want to say they're not equal 1, because it could be. But so there we would look at the probability of a cat, And if that's 0.7, we could conclude, yes, there's a cat in there. And if the probability of a dog is 0.8, yes, there's also a dog there. If both those probabilities are small, then we'd say there's neither there. Does that make sense? So we organize our network in such a way that we have the right inputs and we kind of know how to interpret our outputs. And then we need to figure out what's in the middle and how to train it. How hard can that be? Okay. What's a good approximation? What is a good approximation? And I guess part of it depends on, well, let's look at an example here. So let's say we have here, I've just duplicated this 3 times because I'm going to look at different possibilities. So we have a 2-dimensional values for circles and triangles, right? And these are different classes, right? And we're not defining what the axes are exactly, but we're trying to come up with a way to separate those so that we can say on one side are the circles and on the other side are the triangles. So we're trying to come up with a function, or in our case it'll be a relation, let's say. And so let's look at one possibility. Let's say we do a line. So the question is, which line would give us the best separation? And I'm going to claim it's something like that. It is a very wobbly line, but it's a line nonetheless. How good an approximation is this? Is it perfect? Now, why is it not perfect? Because, yeah, we have 2 red dots up here, and we have a triangle, 3 triangles down here. So those are clearly wrong. So that's imperfect. Okay. Let's look at another possibility. So let's say, well, we don't like that, obviously. A single line is not going to do. And there's no single line that's going to separate here, right? We don't have. We can't separate based on a single line. But I can come up with a perfect separator. Okay, let's see, how do I do this? I can also come up with an imperfect one. Let's see. There we go. Now, how is my error here? It's 0, right? I am perfect. This is a perfect approximator for these inputs. Now the question is, how well do we think this generalizes? Really, really, really poorly, right? Assuming kind of what we look at and think that there are going to be a lot of triangles kind of over where these triangles are and a lot of circles over where these circles are. Right, and it may be that these circles are, right, there are a lot of possibilities of why we have these outliers. Give me one. An error. Bad data? Is this possible? Yes. So it could easily be bad data, right? You may have sent these might have been images, and you sent them out to Mechanical Turk. How many people are unfamiliar with Mechanical Turk? Okay, Mechanical Turk is Amazon's service that allows you to rent human cognition, let's say. So you can send out problems to humans to solve. And so it's for a while was the best way to solve CAPTCHAs, right? So that, and so we might have sent out these pictures, and let's say these are cats and dogs, and we sent them out to a bunch of Mechanical Turk people who are paid half a cent per image that they classify. And some of them, for some reason at 0.5%, aren't perfect, right? So they get some wrong, which is why you often will do best 2 out of 3 or something like that. So there can just be errors in the data. It could be a freaky cat, right, that looks very dog-like. And so it fooled the humans. Yeah, those are some possibilities. There's been use of deep learning with radiology images in terms of diagnosing. I don't remember the sorts of things you diagnose on those images, but there's stuff that radiologists diagnose, right? That's why they get paid the big bucks. And in some cases, neural networks can do better than humans. Now here's the question. How do we know that? I mean, how is it better than humans? Like we took what a human did and then we said, oh, we're different in these various ways, but don't worry, we're better than you are? You got it wrong? How do we know an incorrect labeling of something? So let's talk about it. It's radiology, and we're going to, what are we going to look at? Diagnosing, let's say, cancer in the brain, just to make it bad. Okay? And so we've got a particular image, and Joe radiologist, Dr. Joe, said, not cancer. And our neural network says, cancer. How can we know which one's right?
Eventually it will become a lot more.
Okay, so actually that's one way, is go beyond what the human looked at label, right? From the autopsy, we can determine, right? Yeah, the problem is it's destructive, the autopsy. So another, yeah?
I would think since it's deep learning we are talking about, we would consider feature extraction. So why did the doctor think there was no cancer? And then we look at what the algorithm says is why it thinks there's cancer.
So that'd be so nice if we could say to the algorithm, why do you think that this is, whatever I said, cancer, right? And it could come up with an explanation. And there are certainly a lot of machine learning algorithms that do have explainability. So random forests are an example you can go through with. Unfortunately, that's one of the limitations of neural networks. It's like very hard to come up with any explainability, and that is an open research topic. How can you do that? Okay. So good idea. What else can we do? Well, yeah. Yeah, don't just ask Dr. Joe. Ask Dr. Jim and Dr. Julie and Dr. somebody else, right? And get a wisdom of the crowds kind of thing. But you don't just ask random fairgoers. You want to have experts, right? So everyone would probably agree that if you have 10 radiologists in a panel, that the consensus, consensus I guess means everyone would agree, right? The vast majority, let's say. If the vast majority agree, then that's probably the way it is. But the ground truth is not what the human says. It really is what's actually going on in there. Okay? So obtaining labeled data can be very difficult, and obtaining clean labeled data can be difficult. We saw even in the cats and dogs examples, where there was really what I would think of as not clean data. Like a cat and a dog. Come on now. Or a logo for some animal service. So let me come back to here though. So let me come up with another model that's slightly more complicated than our line and slightly less complicated than our high degree polynomial here. So let's try a quadratic. So unfortunately I'm doing this by hand, but I'm kind of How does that look? Again, it's very wobbly, but does this, it certainly has somewhat less error, right? We have the same red circles which are incorrect, but we only have one incorrect triangle rather than the 3 incorrect triangles. Okay, so that part is good. But we already decided that just looking at that is no, because we can come up with 0 errors. The second question is, does this seem like it will generalize well? And it seems like it will generalize well, yes. So the way to really tell would be to generalize, to try and get more samples from my data and see how well it works. So this up here is called underfitting. So we are not fitting our data as well as we could. Our model isn't rich enough. We don't have we don't have enough degrees of freedom. Okay, based on that, what's this one called? Overfitting, exactly. Overfitting, you get really good accuracy on the data you've seen so far. And a way to think about this is it's effectively memorizing, right? It's memorizing the exact inputs that are coming in so it can be tuned just for those, right? So there might be, in this network, something that kind of says, let me figure out what this red one is, right? I'm going to characterize exactly what that red one is, and I just have a special case that says, oh, that one is a red, right? Even though everything else about it kind of looks blue. Okay, and we don't have a name for this. I'm going to just make one up now. Right fitting. Right? Okay. Questions? Can we tell a priori what sort of a model we need? Not very easily. What we instead have to do is look and see kind of how it's doing. So, as I said, we don't want to just fit what's there. We want to generalize well to similar data. That's the whole key of this all, really. You might think of it sort of as the difference between, you're familiar all with hash tables? Okay. Didn't even know the etymology of a hash table. Where did the name come from? So there's a function, yeah, and it's called a hash function. Why is it called a hash function? And how many people here have had corned beef hash? All right, so corned beef hash, the day after they serve corned beef and potatoes, they take the leftover corned beef and potatoes and they chop it up, right? You take your corned beef, you go this way and this way and this way to make cubes, right? And you do the same thing with the potatoes and the onions. And then you smoosh it all together to one very nice mixed up, like all cut up and then rearranged and separated and put back together. What does that sound like? It's like a hash function, right? That's the sort of thing you want. So in the 60s, I think this was done, early 60s, people would informally talk about hashing, right? Making a mess of stuff, making a hash of something, is making a mess of it, kind of. And it was a little odd that it actually appeared in print and became then the official name. And one of these where then you don't even remember where it came from. All right. So anyway, it's kind of like hashing. Where was I going with this? Two common ways you'll use a hash table. One, you're going to create a hash table and just unknown stuff is coming in, right? You've got a bunch of incoming URLs in a router, and you want to hash them to some value to find out. I don't know what you want to hash them. So you want a nice hash function that's going to spread stuff out nicely and not accidentally have a lot of collisions. What's a perfect hashing? 0 collisions. Can we guarantee 0 collisions? If I've got an input that has n inputs and an output table size that's only m, where n is much bigger than m. No, you can't. But we still talk about perfect hashing, so how can that be? No. If we know our inputs, we can come up with a perfect hash table. And an example would be if you're writing a compiler and you get a bunch of reserved words. How many reserved words are there? I don't know, but they're reserved. There are only a certain number of them, right? And so you can spend a little bit of time, figure out a perfect hash function, and so that's kind of like memorizing or overfitting, right? It works exactly great for these words, but if we have users that can start adding reserved words, then all of a sudden we could potentially be in trouble, right? This hashing, the hash function we used, could work very poorly for those. So, but there are cases where memorization is exactly what you want. So if we have too much freedom, we fit well, we generalize poorly. Too little freedom, both of them are bad. We fit poorly, and we also generalize poorly. And speaking of this generalization, so let's say we have, let's go back to this picture here. So let's say we're using a line. Okay, we're going to just look at, we're going to zoom in on this. This is our problem. Come up with a line to separate these. All right? Are all lines with the same accuracy as good as each other? Because? Okay, yeah, you want to generalize well, and therefore you want something that separates. So let's go ahead and do blue here. So here's one possible line. And we'll do another line. So that's the purple line, and we've got ourselves a orange line. Which do you like better? Which has the highest accuracy on the test data? They're all the same. Which do you think would generalize better? I would claim the orange one, right? I mean, you don't have any reason to believe that that line should be closer to the orange or closer to the blues, and so you might as well put it in the middle. And that's what support vector machines do, right? Those are kind of machine learning, which basically says, as you said, maximum margins, right? That's the idea. Was there a question? Thank you. Okay. So we want models that generalize well, and some models do better than other models. So how are we going to tell whether we fit well and whether we generalize well? Because if we fit well and we generalize well, what does that say about our underfitting or overfitting? Well, if we generalize well, they should be good, right? So here's our, how we're going to tell. We're going to have data sets. Okay, so this is some, for the cases we're talking about, we're labeled, right? So we have, or another way to look at it, is these are going to be XY pairs. Okay, so we have a bunch of these. And the X represents? That's their input. So it could be something simple. It could be 300 by 300 by 3. It could be a 30-second audio snippet, right? Where we're trying to come up with a transcription or predict what song it is or, you know, the genre or something like that. Right? So there could be a lot of data there. And the Y is the output, the desired output. So this is what's called a supervised learning problem. In a supervised learning, we have X and Y. In an unsupervised learning, we don't have the Y. Or maybe we can have semi-supervised where we have a y for some. So a clustering problem would be an example of unsupervised learning. Find good clusters for this. So we've got our training data, and this is the data that we use to generate our model. That was the data that we saw on the graph with the triangles and the circles, right? So we go through and we try and fit our model, right? Learn weights, and then what can we look at based on this training data? What is of interest to us? How well we do. So how good are we? Right? And we can look at the training. Well, we could look at accuracy. Normally what we actually have is a loss function. So this is the thing that we are trying to minimize. Because basically this is a giant minimization problem where we're trying to minimize the error from our true function, or at least the true function on the particular training values. So this will tell us if the training loss is high and doesn't get down very low, what will that tell us? Underfit. So high loss means we're underfit. We don't know much about neural networks now, yet, but for the little we know, what could we do to make our model more powerful? Adding more layers. So in this depth direction, that's one way to make it more powerful. Another way to make it more powerful? More, right? Any given layer, we can decide how many neurons we have, and we can increase those. And one other we can do is, if we look at a weight going from layer I to layer I plus 1, not all connections are there. So a fully connected neural network has connections from every neuron at layer I to everyone at layer I plus 1. They might not all be there. So adding more connections can also increase our power. So we can have a more powerful model. So more layers, more neurons per layer, or more connections. Does that make sense? So the first thing, you don't even worry about generalization. If you can't do a good job of the examples you're given, you're unlikely to be able to do a good job on generalizing. But once you have reasonable results on your training data, then you want to say, okay, we know we're not underfit. Now we want to know, are we overfit or not? And so what we do is use a validation set. So we have another set of data, x1, y1, to, let's say, xm, ym. Where do we get this data? Well, normally what happens is you get one big pot of data, and you break aside some of it. And you say, okay, this will be our validation set. How do you pull those apart? Do you take the last m of them? No, you better randomly choose it, right? So this will be a random subset, let's say, of the single initial data set. Okay, so this is called a validation data set, but it's sometimes, unfortunately, also called a test data set. And that's kind of confusing because now later I'm going to describe what a test data set is. So the validation data set, you then measure and see how well does your trained model work on the validation set. So you test the validation data set on your model. If your training data set is getting 95% accurate, what would you expect your validation? What range could you expect your validation to get? 0 to 99?
0 to 95.
Okay, you left off, so the total possibility could be 0 to 100, but you said 0 to 95. Why?
Training accuracy is 95.
Because what?
Training accuracy is 95.
Your training accuracy is 95. I agree. My question though is why could the why would you not expect the validation to be 99?
Because it's probably not there. Like generalize better on things that you've already previously seen before.
Yeah, you're not gonna it's very unlikely you're gonna be generalizing better than your training. It's possible because this is random and so on, but you would not expect your validation to be better than your test. Normally your validation is worse than your test, or certainly no better. Could it be 20% accurate? And if it were 20% accurate, what would they say about your model? You overfit, exactly. You did really good on this, and you overfit. So if the validation loss is much bigger than the training loss, that implies overfit. Where overfit is an adjective here, right, and not a verb. I'm not telling you to overfit. It is overfit. So what do you do then? Reduce the power. So how can you reduce the power? You could reduce the number of layers, reduce the number of neurons per layer, reduce the number of connections, or change your loss function. Change your loss function to penalize you for complex models. I'll show you an example of that in a moment. Okay? So you will have this cycle where you're going to go through, you have your model, you check to make sure that you're not underfit, and then you check the validation set to make sure you're not overfit, and usually you are overfit and you need to go back and again and again and again, and you're adjusting hyperparameters of your model. The parameters of your model are the weights. Okay, that's what gets learned. The hyperparameters are things you have control over. Okay? Like the architecture of the model, how deep it was, what connections you have, and so on. Okay, and the loss function. So you do this all, and let's say you do this. You have access to a lot of machines with GPUs, so you could do this. You could do a lot of cycles. So you do this 1,000 times, and then you get something that looks good. And now your question is, okay, I've got this final model. How well does it generalize? Well, is it valid to just say, well, I'll just look at the last run of my validation? Why not? Yeah, I carefully chose my hyperparameters such that they would fit the validation data well. And so now all of a sudden I don't know how well we're going to generalize. So what do? I back up one more step and say, well, at the beginning I should have set aside even more data. And that's your holdback data, also called your test data. When someone says test data and you don't have any other information, it's ambiguous as to which one this is, although it's slightly more likely it's this. So the test data only used once. All right? Here's what happens. You do it, you run all your validations, you go through over and over, and then you've got your article all written, right? You're going to publish, and at the very end you look at the, the accuracy of this model, and you're going to run it on the test data, on this holdback data. And that should be a reasonable prediction. Yes?
In the case that you overfit for your validation set and you want to retune your hyperparameters, do you go ahead and retrain your model based on the training data to adjust the weights, or do you just tune the hyperparameters for the validation set itself?
So the hyperparameters, that's a good question. Your model only learns based on the test set. So the validation set is used as a way to decide how to tune these hyperparameters. And then once you tune the hyperparameters, you got to rerun and relearn. Okay? So you're continually relearning on the test data. Okay. How big should these be? Just to give you kind of a rule of thumb, let's say if we have less than 1 million samples, we might do 80% test, 10% validation, and 10%. 80% train, 10% test. Does that make sense? Now, if you wanted a chance after having gone through those 100 iterations of your validation, and then you go through and you run in your test set and you realize, oh my gosh, this doesn't generalize well. Unfortunately, you used all your data now, right? So what do? Well, you wish you'd saved aside 5% at the very beginning that you could use as yet another level of holdback, right? So you can go through and try and do more stuff and eventually see. This, to me, seems similar to, are people familiar with the term p-hacking? So in psychology, it's sort of bad. It turns out that many, many experiments are not replicable because the nature of what happens is people do experiments, and if they do not get a significant value, that is, p is not less than 0.05, then what do? They don't publish, because no one wants to publish. Yes, there's nothing going on here. So they just file it away. And every so often they get a significant result, and those they publish. Well, if you're doing that, with a significance value of 0.05, you'd expect every 20 of these experiments to yield a significant result. And it looks like that's kind of what happens. All right. So bias and variance are terms that really have to do with underfitting and overfitting. So high bias is underfitting, high variance is overfitting. Give you kind of an intuition of this. So if we have a chart here, high bias and low bias, and high variance and low variance. And I am going to use someone who is doing target shooting. Okay, right, they've got a rifle, they're doing target shooting. Here's our target. I am embarrassed to say, by the way, that it was only about 5 years ago that I realized what Target's logo meant. So, anyway, I just thought they had some circles. I didn't know. So, high bias, low variance. That would mean we had what would be called a tight grouping. So we take our shots and they're all close together. But where are they not? In the center, right? And what does that mean? Is there a fix for that? Yeah, I assume, adjust your sights or something, right? Presumably that's what zeroing it in means, is so that when it's aimed at the center, it ends up at the center. So low bias, low variance, of course, would be right in the center and a tight grouping. Low bias, high variance, where's the center? I mean, it's centered around the center, but it's kind of all much larger grouping. What could cause that? Yeah, shaky hands, you're not very good. You need beta blockers, which I guess those guys take that to help with shooting. stuff about maybe you need a longer barrel or something, right? You're shooting very far away and it's going to spread and I don't know. So it could be either basically the operator or the equipment. And then high bias, high variance is kind of the worst of all possible worlds, where you're not very tight grouping and you're far away from the center. So we're sort of showing here in this low variance case is we're generalizing well because our variance, the analogy here is our variance is really the result of running our neural network on tests or on instances that were not part of the training set. Okay? So if they all kind of fit in very well, then we have low error and that's good. If we have high variance, then that means it didn't generalize well. Okay. Signs of underfitting. How do we know it's underfit? High training error. And a lot of times what we can do is look basically at a training schedule. So look at this is the error, sorry, this is the loss. High training error is exactly the same thing as, yeah, training error or training loss. So over time what we expect to happen is we get something like that. So this is, let's say, number of epochs. If we run more epochs, would you expect the training error to go down? Yeah. Because our whole goal is trying to minimize the loss. And so we're trying to adjust our weights such that our loss is going down and down and down. Can we reach a non-zero plateau eventually? Sure. There's unavoidable bias. Right, there's unavoidable errors, like humans. So we could read, let me show an example here. So somewhere here might be, let's say, human error. And ideally, we'll get below human error. We'll get better than human error. But we still are probably not going to get to zero. And in fact, we don't want to get to zero. We would like it so that if there was a miscategorized, right, a mislabeled test set, that it just got that wrong. That would be preferable to it getting it right, because that would mean we're overfitting. So high training error loss is really our sign of, that is the sign of underfitting. And for overfitting, our sign, high validation error with respect to, with respect to training error. So this is validation error bigger than training error. And what we can do as well is construct, again here, this is our error, or our loss, and this is our epochs. And we know that for our training, our training error looks like this, right? What does our validation error look like? We don't expect it to ever get less than the training error. We're going to start out probably higher than the here. And we're going to go down. Maybe we'll approach it. And then what will happen? It'll get back up. Now, there's a discontinuity here. It should be a smoother type thing here, right? So what we're really doing is eventually overtraining, which means we're overfitting. So that is another thing that you can do to prevent overfitting. Stop early. Okay? Don't do so much where the validation error goes bad. Does that make sense? All right. How can we reduce bias? I think we talked about this a little bit. Bigger neural network, fine. A new architecture. So convolutional neural networks or a new architecture, we're going to talk about that in a lot more detail. Train longer. That's always going to reduce the bias because of our design, which is that every epoch we're going to reduce the training error. Reducing the variance. Don't try and reduce the variance until you've addressed the bias, right? Until you've got good training error, ignore how well it generalizes. The biggest, well, there are two really big ones, but one very big one, and this is why neural nets have worked so well in deep learning the last 5 years, is more data. Why would more data tend to prevent overfitting? Say that again? The impact of a single outlier is much less, yes. If you imagine, if we go back to the polynomial case, right? If we have 100 points we're trying to fit, and we allow a polynomial of degree 50, then if we have 10,000 points, then it's just not going to have the same flexibility to really, jag that thing around into weird places. Regularization. So this is, I'll mention that in just a second, and new architectures can work. So for regularization, here's a basic idea. One way to do it. Penalize overly complex models. So that is, your loss function is going to take into account not just at how well you do at classifying the samples, but also at how complicated the model is. So our function is going to be, our loss function is going to be different now, and the minima are going to be different. Okay, so our minima, our minimum may be something that has less high accuracy, but has a much simpler model. So the idea is, let's say we have a polynomial and we're trying to minimize sum of square errors. Okay. So yi minus y hat I. So yi is going to be the true value of the ith training sample, and y hat I is our predicted one, right? What the neural network came from. So instead of just minimizing this, we're going to minimize, let's say, that sum plus some constant lambda times the degree of f. Yeah. Well, yeah, there are a couple squares missing there, for sure. So we could do something based on the degree of the polynomial we've come up with. What should this value of lambda be? This is a hyperparameter, right? It's lovely when you're doing deep learning because you have so many hyperparameters, and then there's a question of how do you search over the hyperparameter space to try and find something good. Or what we might have is, let's say, the sum of the squared error plus some lambda times the sum of the coefficients of our polynomial. Okay, so this would tend to want to have small values, right, for our coefficients. And certainly wouldn't want to have a large number of terms with large coefficients. Does the concept make sense? So we could do something similar to that as we are working with a neural network in terms of coming up with what error is. But more likely what we may do with a neural network is in our layers, we can add some regularization. We'll talk about that in more depth. Or something else we can do, which is interesting, is called dropout. That is, we've got these weights, and as we feed in a training example, we're going to say, let's just kill off half of the connections. So when you learn, you're learning on a degraded network. And then the next sample comes in and says, let's pick randomly again, 50% of them to kill. Okay? So we may do that on particular layers or throughout. Often it's designed sort of layer by layer. So that's a way to regularize. So it forces the neural network to not overly tune for a particular data set. Because the next epoch, when you come in for the same training example, it might have different connections that it can use. So it's going to be very hard for it to memorize this one circle way up here. I'm going to treat totally separately and have its own little path. Okay, features. Features are just a general part of machine learning algorithms and used to be much more important. So if you're not using deep learning, features are critical. Engineering features to determine what to use is critical. So in the past, for image recognition, you didn't feed into your machine learning algorithm the pixels. That's craziness. You instead might have an edge detection algorithm, right, that would go through and do an FFT or something and come up with edges. And okay, we will carefully figure out what those edges are and feed them in. And then we would have other features that you'd carefully handcraft. And then those features would be fed into a machine learning algorithm. In our neural network, in some sense, those features can exist, but the neural network has learned them. And they're at some number of layers into the neural network that it may have learned edge detection if that was important. So it may have learned to find diagonal edges and vertical edges and horizontal edges and so on. And so it's much more common in deep learning to just feed in the raw data. But sometimes it makes a lot of sense to feed in extra data. Let's say you're doing a sales forecasting problem, and you're given sales numbers for various stores. So you have dates and sale number, date and sale number, and so on, what got sold. Well, it might really be useful if you just feed in the raw dates and values. It would be very hard, if you had enough data possible, but hard for the neural network to learn which days are holidays and not. Or even, might be somewhat difficult to learn which days are weekends versus weekdays. So you might adjust your input rather than just putting in the raw date. You might also put in the day of the week and the day of the month. Well, we already have day of the month. Day of the week. And is it a holiday? And maybe even how many days since the last holiday. You know, some things like that. Okay. And that could allow the neural network to learn much better, especially if your amount of data is limited. If you have huge amounts of data, it's amazing what it can learn. But you can help it out quite a bit if you don't have huge amounts of data. Okay, I'm going to skip this a second, and I want to show you, let's see. All right, here's what we're going to do. We're going to try making this work. So I am going to show you how we get the actual Jupyter notebook running. So we're going to go to colab.research.google.com, and we get to create a new notebook. And this is great. We have a Jupyter notebook in the cloud, so we can do stuff like print 3 plus 4, and we get eventually, hey, it's an interpreted language. Okay. I'll tell you what, let's turn on the GPU and see if it helps. So we'll change the runtime type such that we have a GPU. Yeah, so it's not the fastest thing in the world. And now we're going to go to Clouderizer. So Clouderizer provides us a better way to really manage our Jupyter notebooks that could be running different places, like could be running on Collaboratory on your own machine, or on an AWS instance, or a Google Cloud instance. And by the way, I do have $50 certificates for Google Cloud platform for you guys to use. So I will distribute those at some point. So here's what I can do. I can create a new project. No. I'm going to go to the community project. Oh, don't make me annoyed. Okay, so community project, and there's a community project called CS152. And so we'll call this CS152, and it's going to be on a local machine, right? The two choices are AWS. If you use AWS, it'll spin up an AWS instance for you, which is really nice, but it costs money. So the local machine doesn't. So we're going to say local. There's a bunch of packages that get installed. There's some data that gets loaded, some code that gets loaded from GitHub, and here I'm going to sort of name this project CS152. This is where the output is going to be in Google Drive. So it's going to store this all in Google Drive Clouderizer. All right, so I create my project. And then, next steps. On Linux, which is basically what the Collaboratory is, we're going to go ahead and run with an exclamation in front of it to say that this is a shell command as opposed to Python. Run that. And it's now going to do some chugging, right? Because it's basically going to create, I think, using Docker. If it's on a local machine, it definitely uses Docker. It might do something slightly different in Collaboratory, but it basically creates an environment. Is that in this room? It sounded like a jackhammer in this room. All right. So it goes ahead and does its thing. If we close this, we will see we have the CS152, and it's going ahead and running and installing packages. Okay. In about 10 minutes, it will say that it is running. And then we can open a terminal window and basically have SSH'd into the machine and click on Jupyter, and that will open another window where we have a Jupyter notebook, which is different from this Jupyter notebook. This Jupyter notebook is the raw Collaboratory Jupyter notebook. The Clouderizer Jupyter notebook is within this environment, which we started running in Collaboratory, its own Jupyter notebook. Okay? And it's a Jupyter notebook hooked up with Google Drive, initialized with a GitHub directory, and so on. It's not that exciting to watch this. Wednesday, hey, it changed. Did you see that? It is exciting. I take it back. So Wednesday, I will run it again at the beginning of class. And then we'll go ahead and run the dogs and cats. But I still have 5 minutes, and I'm going to use them. Don't worry. So we're going to run the dogs and cats, and then actually take some test data that Kaggle provides, unlabeled pictures, and label them and submit them to Kaggle, and basically see how we do. Kaggle, let's take a look at that. All right, so we have here an overview of the dogs versus cats. It describes it in 2013. They had a dogs versus cats competition for fun, which means you didn't get any money. And they wanted to kind of bring it back and see how people are doing today. So when you have a Kaggle competition, first thing you have is data, right? So you have a sample submission that shows when you are submitting, what's it going to look like? In this case, it's a CSV file that's going to have an ID and labels. So the test data that they're going to give you is a bunch of JPEGs, ID number.jpg. And you then are supposed to come back with the label, which somewhere it tells us is supposed to be the probability it's a dog. And then our training example has a bunch of cat pictures and dog pictures. So 25,000 cat and dog pictures. The cats start with cat dot, the dogs start with dog dot, and then there's a number in there to uniquely identify them. This is different from the format that we had, right? Remember the format we had? We had train and then cats and dogs, and within cats and dogs we had just JPEG files. That's because this was pre-processed to be easier to use. And we had also a valid directory, which was our validation data. And a test directory, which was these test values. So under the test directory, there was no cats and dogs. Because if you already know what the labels are, it removes a lot of the surprise. So just the raw pictures. But we broke apart from our given training data a subset of data to use for validation. Okay. And then when you submit, so let's see, the first thing is somewhere here, it's going to tell us how we're being judged. Evaluation. So we're going to use this log loss, which we'll talk about in more detail, but it works better than sum of squares, basically. Okay. So the log loss is going to be low if we correctly predict, and it's going to be higher if we predict incorrectly. So we submit a probability the image is a dog. So for instance, these are 3 IDs that we're saying we have no idea which it is. The leaderboard, so what happens is, there's a public leaderboard. So the public leaderboard is on the test data that they gave out. All right? So you can see what the loss is, and you can see, compare yourself to others. If you've got a competition that's currently running, as opposed to this one, which is over, then you can submit, and when you make a submittal, it'll show up on the leaderboard with the particular value. And if you have a for money competition, you want to be towards the top. After the competition ends, though, there's a private leaderboard that is held back data that Kaggle never gave out to anyone, that they will then run. It's after the competition is over. So how many times are they going to run it? One time. What does it sound like? Right? This is this holdback data, except it's this one more level that I talked about. Because if you can look, the number of entries here, this guy did 435 entries to the leaderboard. Guess what? He's doing okay now. Is it possible he's overfitting to the test data? Yes, it's quite possible. And so therefore, we have this separate, it's only going to be run once, and that's what's actually used to find out how people do. So what we're going to do on Wednesday is I will go through, I'll make a submission for dogs and cats so you can see it. And this will be in preparation for your first exercise, which I think we're going to do in pairs. Tell me how that sounds. Which is going to be a slightly more complicated problem, which is instead of just dogs and cats, it's 120 different dog breeds. So you get given a bunch of dogs, 120 different dog breeds, and you're supposed to evaluate the dog breed. Questions? I don't know. What would you like? I don't know. I will decide by the time I hand out the first homework what it'll be. So, okay. See you on Wednesday.